Hello there. We're going to look at today in the OpenStack Adams First textbook, looking into Chapter 4 here, Chemical Bonding and Molecular Geometry. We're going to start off with a brief overview on ionic bonding, a brief overview on covalent bonding. Then we're going to talk a little bit about nomenclature, and that's probably as far as we'll get in this video. Later on, we'll take on the rest of the chapter, so let's start with this. So here are some images of some common objects here. You see the soccer ball in the middle. The thing on the far right is a radar tower that is, I guess, located near Tucson, and it's a little hard to see, but the radar tower has kind of the same shape as the soccer ball, and you see the soccer ball's got a 5-membered section right here in the middle, and then there's 6-membered sections around it, and a repeating pattern of that. Well, that actually, long after a soccer ball was created, someone discovered the existence of this kind of compound right here. These are all carbon atoms. They're all sp2 hybridized carbon, we say, which we'll explain more about what that means later on. But this is a form of carbon that's called Buckminster fullerene, or a fullerene molecules, and those were discovered quite recently and have some very interesting properties. And you see here, maybe you can see that there's this kind of thing here that looks like two things together, and if you look at that, that's one. Those are double on the bottom and single on the top bonds, and then the balls represent the carbon atoms. Alright, so we're going to start off now really talking about ionic bonding. We've talked quite a bit before about cations and anions. Remember that typically for monoatomic, that is one atom, ions, we're going to usually go for a noble gas electron configuration. So if you're looking at nitrogen, oxygen, fluorine, neon here, this is a little bit of the periodic table. Neon is our noble gas. Fluorine will pick up one electron and form F- fluoride. Oxygen will pick up 2 electrons and form O2- in the superscript there, oxide. And nitrogen will frequently pick up 3 electrons and form N superscript 3- nitride. And again, whether I say O2- or O-2, that's the same thing there. On the cation side, if we go back over here after neon, the next element is sodium. Sodium is element 11, neon is element 10. Sodium can give up 1 electron, right? So minus 1 electron, and that gives us the sodium +1 ion. So we know that group 1 tends to be +1, group 2 tends to be group 1 tends to be +1, group 2 tends to be +2. Over here, this is group 18 is the noble gases. Fluorine is in 17, oxygen's in 16, and nitrogen's in 15, and we can kind of generalize that those tend to form, 17 tends to form -1 ions, 16 tends to form -2 ions, and 15 tends to form -3 ions, although there are some exceptions for those. We also, back in Chapter 3, looked at a periodic table which had some of the transition metal ions in it, so you may want to refresh your memory on that. So what we're going to try to do is try to predict the charges of these common ions that we encounter and write the electron configurations of them and then put them together in compounds. Here is an example that's often used to illustrate the strange things that happen when you have bonding. So right here on the left, this kind of creepy looking thing here is actually sodium metal. That is a metal that's in an oil, and the metal's very soft. You can cut that metal with a butter knife, just about tear it with your hands, although I wouldn't advise touching it with your hands. but it's very soft metal. It looks kind of grody on the outside because the little bit of reaction with the environment with oxygen forms kind of an oxide layer. If you cut it open, it's quite shiny. And then if you look at B here, this guy right here, that's chlorine gas. It's a toxic gas. It was used as a gas weapon in World War I. It was the kind of the original gas weapon. Yellow-green gas, not a pleasant thing to inhale. So neither one of these things are something that you necessarily want to be around. But if they react with each other, they form this compound right here, C, table salt, which of course you put on your French fries, and it's only dangerous in that it can contribute to high blood pressure. So quite a safe compound for us compared to these other two elements. And so that just goes to show you that when you form compounds, the compounds can have quite different properties from the elements that they are formed from. Here is a molecular level view of sodium chloride. On the right, we have the blown up sort of structure where you can see that you have your purple sodiums and your green chlorines, and they're in an array, a three-dimensional array that looks like a cubic sort of array. And if I think about, for example, this sodium right here, he's got 1, 2, 3, 4, 5, 6 chlorines around him, if you focused in on any one chlorine, you'd find that it also has 6 sodiums around them. So one of the things that we talk about with ionic compounds, although sometimes we'll use the word molecule, that's not really appropriate. We really should use the word formula unit. But people will say molecule, and folks will use it. So it's because it's kind of hard to say, does this sodium go with that chlorine, or does that sodium go with that chlorine over there? Which one would be the molecule? So it's really a formula unit that expresses the ratio of the elements in it. A is probably the more realistic view of this, where you're looking at the ions where they're actually touching each other. So it's the same view, it's just not kind of blown up and expanded so that we can see better what's going on. A lot of understanding chemistry is being able to imagine these representations of matter at the atomic molecular scales and being able to work with those. So covalent bonding, we're going to talk about that briefly. And covalent bonding, unlike ionic bonding where we form ions, in covalent bonding we share electrons to get a more stable arrangement of electrons. And we'll talk more about the nuts and bolts of doing that in probably our next video. So we're going to describe how those form briefly, and then describe this concept of electronegativity and polarity, and work with that just a little bit. So figure 4.4 here is one that I really like. This is a graph of the energy. Here, let me blow it up a little bit so we can see a little bit better. So the y-axis here is energy. Okay, and this line right here is 0, which means that there's neither favorable or unfavorable interaction between these two atoms that you see up on the top. The x-axis is the internuclear distance in picometers. That's sometimes called R. That's just a symbol for that, the distance between the two atoms. And so what we see is at a very large distance, when they're far apart, the two atoms don't interact with each other, and the energy of that interaction is 0. Then as you start putting them together, eventually they begin to interact, and we see that interaction is favorable, right? And eventually this goes down and gives us, a value here at the bottom of that curve of negative 7.2 7.24 times 10 to the negative 19th joule. This is specifically for hydrogen, for a hydrogen molecule. But then if we try to squeeze these things together, closer and closer together, unfavorable terms come into play. The energy rises and eventually becomes unfavorable. And so this is very hard to squeeze two hydrogen atoms into the same space. And you may say, well, that never happens. But it turns out that in stars, such as our sun, you have a nuclear reaction that occurs where you have 4 hydrogen atoms combine to give a helium atom, and plus a couple of, I believe they're they're positrons, I think. I think we have 2 of those. Anyway, this is the fusion, the main reaction that's nuclear fusion, I'll call it. Nuclear fusion, it's a nuclear reaction. This happens, it happens in our sun, and if it doesn't happen, then the sun doesn't produce the light and energy that we rely on. So, I mean, this can happen, but it's really hard to cram those hydrogen atoms together. That would be way, way, way up here when you're cramming 4 hydrogen atoms together. Very energetically unfavorable, so very hard to make this happen. The way the sun makes it happen is the sun is simply so big and so massive that its gravitational forces are able to overcome those forces of repulsion there. But that's getting away from the chemistry and into the physics. Let's go back to chemistry now, and let's talk about the bottom of this curve. So this bottom point of this curve, this is the most stable length for a hydrogen bond. It's 0.74 picometers, right? So 0.74 picometer. A picometer is 10 to the negative 12th meters, so that's if I convert that to 10 to the negative 12th meter per 1 picometer would be one way of doing that. So that would be something like 7.4 times 10 to the negative 11th meters, to give you a sense of how tiny that is. But that's one unit that we use for bond distance. At the energy of that bond, this negative 7.24 here, if I want to break that bond, that energy, I have to put in that same amount of energy to bring it all the way back up. So that would be 7.24 times 10 to the negative 19th joules, and that is per atom. We could multiply that by Avogadro's number and get so Avogadro's number is 6.02 times 10 to the 23rd atoms per mole. And then that would give us, so let's plug that in the calculator and see what we get here. This is going to be the energy to break 1 mole of hydrogen bonds. So I'm putting 7.24 second comma to do times 10 to the 19th. Negative 19th times negative 19th. Then I'm going to multiply that by 6.02 second comma 23rd, and that gives me 435, 848 if I count all those, carry all those numbers. That's joules per mole. If I want to convert that from joules to kilojoules, then I'm going to say 1 kilojoule over 1,000 joules. That's going to be 435.848 kilojoules per mole. That's called the bond energy, or the bond dissociation energy for that hydrogen single bond. So that's what that energy is, and you'll deal with that when you get into general chemistry more. But I think it's a good image to keep in your mind of how that occurs. Here is a diagram showing a compound of hydrogen and chlorine. Hydrogen and chlorine, as we'll see later, this would normally exist as a gas and be called hydrogen chloride. So that's when it's the gas. And if we dissolve it in water, it's called hydrochloric acid, which is probably the way we encounter it most. Very common acid that we work with a lot of times in the lab. Now, when we look at this, so this is our hydrogen and our chlorine on the left here. This is a electron density plot, it's sometimes called an E-plot, electron density plot. And what you see here, usually they use red for electrons. I don't know why this one's green, but this over here where it's dark is high electron density, which means you see a lot of electrons there, or a lot of probability of seeing electrons there. And then over here where it's lighter, this is a low electron density. So electrons are negative, right? So what we would say is that this end over here is going to have kind of a positive character to it. This end's going to have kind of a negative character. It's not a full positive and negative, so we're going to use this little curly d, which is the lowercase delta. So we say that it has a partial positive and a partial negative center. This image here is a dipole vector. The arrow goes to the partially negative end. The partially positive end has a little plus on it there. The longer the vector is, usually the stronger the dipole is, so that's another way of thinking about that. And so this is an example of what's called a polar bond. And in fact, this is actually a polar molecule. And the fact that the molecule is polar very much explains some of its properties. Why it, for example, is an acid when it's dissolved in water is a property of that polar bond. There's a lot of details there, but that's one of the skills you'll be developing in general chemistry, is the ability to identify, based on structures, whether things are polar or not. And we'll touch on that just a little bit in this course. Now, how do we tell how well the electrons are shared between atoms? A very useful concept is this concept of electronegativity. Electronegativity, usually I would abbreviate that ENEG, or just EN. Sometimes you'll see that written either of those ways. And electronegativity is another periodic trend, like electron affinity and ionization energy and things like that. The electronegativity trend is that as you go across and up the periodic table, you increase the electronegativity. And fluorine is the top, so we leave the noble gases out of it. And hydrogen is kind of a weirdo because it doesn't quite fit the trend. I always like to suggest students think about hydrogen. Hydrogen would fit right there between boron and carbon. That's something to remember. These numbers, electronegativity is a little complicated because you can't really measure electronegativity directly. There are a couple of ways to try and define electronegativity. Folks have proposed various things, but there isn't like a direct way to measure it. So that's one of the reasons it's usually presented separately. But the concept of electronegativity is actually probably much more valuable to most students of chemistry than any of the other periodic trends. So it's an important one to remember. Fluorine's number 1. It's useful to remember that oxygen is number 2. A lot of times that oxygen, you'll see that there. And again, what this means is that if something has a high electronegativity, it really wants the electrons in a shared bond more than the thing with the lower electronegativity. We'll see some images of that on the next slide. This is Linus Pauling. He was an American chemist. He won 2 Nobel Prizes, one for chemistry and one for peace, which is quite impressive. to earn that much in his lifetime, and he came up with the concept of electronegativity among his many discoveries. Very brilliant chemist. Now, this gets to the issue of how do we tell if a bond is a polar bond or not. And basically, we look at this idea of the electronegativity difference between two atoms. And if there's no electronegativity difference, if it's zero, we say that's a purely covalent bond. The electrons are shared equally. And in fact, we tend to say that if the electronegativity difference is less than 0.4 on the Pauling scale, and that's essentially the carbon-hydrogen bond would be an example of one that's 0.4, that those are considered to be purely covalent bonds. And that's important because carbon-hydrogen bonds probably, if you look at all the molecules in the universe, there's probably more carbon-hydrogen bonds than just about anything else. And then if you have something where the difference is so big, where it's greater than about 0.8, we're going to say that those things are ionic, that the electrons in the bond aren't actually shared, that one atom wins those electrons and has a negative charge, and the atom that lost the electron has a positive charge, and that's an ionic bond. And then between those two values, we have what we call a polar covalent bond, which are those bonds like we talked about in hydrogen chloride earlier, that those bonds are going to be polar. Okay, moving on to what we want to get to today is our chemical nomenclature. So let's talk about that. Now, I've sent you a link to a chemical nomenclature worksheet that I think is really a great programmed instruction system to use. So nomenclature is how we name things, and in chemistry we have to be able to interpret formulas and names and think about what these molecules and compounds and atoms and ions and stuff are going to do. And so we're going to talk about naming a few types of these inorganic compounds. Inorganic means actually it may sound like it means something about not having to do with life. It actually means compounds that don't contain carbon-carbon and carbon-hydrogen bonds necessarily, or at least aren't solely composed of those kind of bonds. So we're going to talk about a few types of these here, and you see them listed. So, running through this quickly, and again, I'm referring you to that programmed instruction sheet that I think is super. The way we're going to name simple ionic compounds is we're going to name the cation followed by the name of the anion. The monoatomic cation is just the name of the element. So if we're talking about NaCl, and if we look back up here at our electronegativity values, let's see, Na has 0.9, Cl has 3.0. So who is going to give up an electron and who is going to get the electron? So this electronegativity of 0.9, electronegativity of 3.0, so this is our En values. Our delta En is, you just put the highest minus the lowest, 2.1, that's greater than 1.8, so this is ionic, right? And who's going to pick up the extra electron? Well, it's going to be the sodium is going to give up that electron, the anion, the chlorine is going to pick up the electron. To name the monoatomic cation, we just give the name of the element, so that's sodium. And for the monoatomic anion, we take chlorine, we get rid of the ending, INE, and we're going to add IDE, so that Cl minus is chloride. And so that's how we do that. There are some polyatomic ions that were listed in the Chapter 3 presentation, and those just have names that you have to know of those polyatomic ions, typically ending in ignate. So here's some examples. NaCl, sodium chloride, we just did. KBr is potassium bromide, that's K plus and Br minus. In calcium iodide, we have calcium 2 plus and 2 I minuses, right? And that we simply say calcium iodide. We don't have to say that there's 2 iodides in that name because we know calcium ion is +2. We know the iodide ion is -1, so the ratio of those is specified. Cesium fluoride, cesium's +1, fluorine's -1. Lithium chloride, again, +1, -1. If we look at compounds that have other ions, sodium oxide, the O is considered to be -2, of course. So we have 2 sodiums for 1 oxide, but again, we don't say disodium oxide, we say sodium oxide because that's implied. Cadmium sulfate, both of those have charges of 2. Cadmium's +2, sulfide is -2. Magnesium nitride, the nitrogen's -3, and the magnesium's +2. So when we cross those charges, we get Mg3N2 for magnesium nitride. Calcium phosphide, similar sort of argument. Phosphide is P-3. And then in a case of aluminum carbide here, the anion of carbon would be 4- because it's 4 boxes over from the neon, from the noble gas. And aluminum in group 13 tends to form a +3 charge, so aluminum carbide has that formula Al4C3. You want to make sure that you understand how those names were arrived at. Here are some examples of polyatomic ions. So C2H3O2- is acetate, right? Is acetate. Potassium is +1. So when we cross those, we get potassium acetate is written here. Ammonium is the NH4+ ion. Chloride is Cl-. The bicarbonate ion, or the hydrogen carbonate ion, is HCO3-. Sodium is +1. Calcium sulfate, calcium is of course +2. The sulfate anion is SO4 2-. Aluminum carbonate, aluminum is +3. The carbonate ion is CO3 2-. Notice how we use the parentheses here to indicate that we have 3 of those CO3-. Again, what that essentially would translate to is Al2C3O9 if we multiplied that through. We don't usually write it that way, but that's what that's implying, is that we've got 3 of everything in that group. Everything in that parentheses has got a -2 charge. 3 of them is -6. 2 times the +3 for aluminum is +6, so the principle of electrical neutrality is maintained. Magnesium phosphate here, magnesium is +2, phosphate PO4 3-. So that's how we arrive at those. And again, note the use of the parentheses. Now, there are a few metals, particularly the transition metals, have different charges, and the way we indicate that is we put a Roman numeral in the parentheses after the name of the metal. So for example, iron, which has the symbol 2, Fe, can either be iron 2 or iron 3. This is Fe +2 and Fe +3. There's an old system where we would name these using the Latin name and the root ik and us for the us for the lower oxidation number or charge, and ik for the higher oxidation number or charge. So that's some example of some transition metals that have different charges. And if you look back at that table in chapter 3, those are the ones that you need to know. So here's some example of those. Iron 2 chloride. How do we know FeCl2 is iron 2 chloride? Well, we've got 2 chlorines that are -1. We've only got 1 iron. We must have a 2+ charge on that iron to cancel out the 2 -1s on the chlorine. FeCl3, again, you've got 3 chlorines that are -1, so the Fe must be +3. So we say iron 3, not iron 2. Mercury, if the oxygen is 2 minus, and I have to have a 2 plus charge on the mercury, and I've got 2 of them, so I've got 2 mercuries. Each one of them is plus 1. That counteracts the minus 2 charge there, so it's mercury 1 oxide. If I only have one of those, then that single mercury must have a plus 2 charge, so mercury 2 oxide. Tin's another example. So with 2 F minuses, tin's fluorine's in group 17. I've got 2 of those. This tin must be plus 2. And with 4 of those F minuses, that tin must be plus 4 for the charges to cancel out. So those are some examples of some ionic compounds with variable names. Sometimes you'll see compounds that have water molecules attached to them. They're called hydrates, and you usually encounter these. The way I usually suggest you think about these, if you ever bought an electronic device, like when you got your computer, your iPad or whatever, and you opened up the box, there was a little packet in there, something that says "Do not eat," usually on the packet, and it is a compound. And it's a compound that absorbs water. So it might, for example, if we look down here at these hydrates, copper sulfate, if I have CuSO4, and just have that single CuSO4, water molecules like to stick to it. So if some water molecules get into your electronic packaging where you don't want it, what will happen is they'll stick to that copper sulfate at the ratio of 5 water molecules per copper sulfate formula group, and so this acts as a drying agent. So this is called the anhydrous form. Sorry, let's start over. Anhydrous form. And this form is called the hydrate. And so the way we name them is described here. We name it the way we normally do, and then we use these so-called Greek prefixes to denote the number of water molecules. The Greek prefixes are mono for 1, di for 2, tri for 3, tetra for 4, penta for 5, etc. So this is copper sulfate pentahydrate, where there's 5 there, and calcium chloride monohydrate, where there's only 1 water molecule attached. And here are those prefixes, a full table of those Greek prefixes. This is Aaron Brockovich, who found that chromium-4, which was used by Pacific Gas and Electric, had contaminated some of the water supply out in California. There's a movie about her. You may be familiar with that. These are some models of the ions that involve that. This is the chromium there, and these are our oxygens in red, which is the typical color for oxygens. And so you have CrO4 2 minus. So this chromium here is, and I think this probably is supposed to be chromium 6, not chromium 4 there. If I look at CrO4 2 minus, okay, I know I've got 4 oxygens that are 2 minus each, and I know the whole thing's got to be equal to -2. Because of that, I've got 1 chromium. So Cr plus 4 times -2 is equal to -2. That's chromium plus -8 is equal to -2. So to get rid of that, I'm going to add 8 to both sides. And that leaves me with just chromium, and over here I have +6. So that's an example of how you calculate the oxidation state of a metal in a polyatomic ion like this. Chromium is one of those ones that has variable oxidation states. That's the tie-in to this. The equation I'm using is that if I do the sum of the charge or the oxidation state, I'll put oxidation state. If you do that over whatever you have, that's equal to the charge. This means, of course, sum. So when we're doing that over all the atoms in the, so I'll write atoms down here. Sum over all the atoms in the species, which is species being a word for molecular ion, that's going to add up to the charge on that ion. That's a principle of electrical neutrality we talked about before. And so that basically is what I use to create this relationship, which eventually settles into a pretty simple algebra problem. All right, if we look at molecular covalent compounds, so if you think about the periodic table as being like this, remember that there is, and that's really not to scale, there is a staircase line over here. These are the nonmetals, and hydrogen up here is a nonmetal. So if we have two elements, binary, that means two elements, that are both nonmetals, we're going to have a binary covalent or molecular compound. We're going to name it, and we're going to use these Greek prefixes. We're going to look at the two elements and pick the one that is more to the left or the bottom. I usually say the furthest from fluorine, and we'll pick that to be the thing we name first, and we don't change its name. The one that's closer to fluorine will change its name to end in "ide." We'll write it last. So oftentimes, if we only have one of the first element, we will leave mono out. Oftentimes you'll wind up with a couple of vowels together, and the A that's in the Greek prefix gets dropped, and you'll see examples of those soon. So here are how we name some things, and I would just like to say that if it were up to me, this is how we name everything, but it's not up to me. But this is the simplest one. So SO2, sulfur dioxide. Oxygen is closer to fluorine, so it gets the IDE. There's two of them, so it gets the di prefix. So sulfur dioxide. If we have SO3, we simply call it sulfur trioxide. NO2 is nitrogen dioxide. N2O4 is dinitrogen tetroxide. Notice we left the A out there. N2O5 is dinitrogen pentoxide, and we left an A out there. Again, notice that until those last two, we weren't writing monos in front of the sulfur or the nitrogen. We just started writing a prefix when we had more than one. BCl3, boron trichloride. SF6, sulfur hexafluoride. Hexa is the prefix for 6. PF5, phosphorus pentafluoride. P4O10, tetraphosphorus decaoxide. And the last one here is misprinted, so it's no problem. So if I have iodine heptafluoride, that's going to be IF7, because hepta means 7, and so that's what that one would be. So typo on the slide there for that one gives us a chance to test that. Okay, briefly talking about acids. We're going to talk about acids are important compounds. The term acid was invented to let us predict some properties. If we knew something was an acid, we know certain behaviors. Even at this point, you probably have associate acid with a certain type of behavior. Acids typically release these hydrogen ions when they're dissolved in water. We're going to learn how to name some of these acids. So one type of acid that we call binary acids are oftentimes called mineral acids for historic reasons. But these are where you simply have two elements. You have hydrogen and you have some element X. And the X is another nonmetal, and we're going to put ic at the end of its name. So we'll take the element name and take the end of the element name off and put ic on it, and then add acid to that, and we'll put hydro in front of it. So we'll see some examples here. HF is hydrogen fluoride if it's in the gas phase. If we dissolve it in water, it becomes hydrofluoric acid. AQ means dissolved in water. HCl is hydrogen chloride gas that we discussed before. We saw the electron potential diagram of that earlier. HCl, aqueous, is hydrochloric acid. HBr, hydrogen bromide if it's gas. If it's aqueous, hydrobromic acid. HI, hydrogen iodide, is a gas and can be considered to be hydroiodic acid in aqueous solution. Less commonly thought of as an acid, but technically an acid. Hydrogen sulfide gas, which is quite toxic, by the way, if you dissolve that in water, is hydrosulfuric acid. But again, that one is probably less thought of as an acid than the other ones that we've written. And again, the other name for these are the mineral acids. Now, there are a bunch of acids that come from polyatomic ions, and those polyatomic ions contain typically hydrogen and oxygen and some other element. Well, the polyatomic ion contains oxygen. The hydrogen makes it an acid. So when we name oxyacids, we're going to start with the name of the anion. If the anion ends in ate or ite, where ate means more oxygens and ite means less oxygen, we're going to replace ate with ic and ite with us, and we'll add the word acid. And that ic and us that we talk about are the same suffixes I mentioned before in that old system where we called iron plus 3 ferric and iron plus 2 ferrous, because ic has the higher oxidation number. We see here that ic has more oxygens than the version ending in us. So that's consistent. And then we put the word acid on the end of it. So here are some examples of those. And I always like to just run through an example of this. There is kind of a system to it. So if I think about ClO3 minus, that's called the chlorate ion. And if I want to turn that into an acid, I'm going to add a hydrogen, an H plus to that, and I'm going to add as many H pluses as the negative charge. So that's 1. So HClO3 will be the acid version of that. Now I'm going to take the 8 off and say chloric acid. If I have one less oxygen, that's called the chlorite ion. To make it an acid, I still add one hydrogen, and that's the chlorous acid. There's some prefixes we can add. If I go down one more oxygen, that's the hypochlorite ion, which we mentioned in the last video was in bleach, and that's HClO would be the acid version of that, and that's called the hypochlorous acid. If I went up one from the chlorate ion, that's ClO4 minus, that'd be called perchlorate, per meaning more. And if I make the acid again, I'm just adding the same one hydrogen to that, and that would be called perchloric acid. So there is kind of a system associated with this. The problem is that you have to remember one of these to put the rest of them there, because it's not like if I look at sulfate, SO4 2 minus would be the sulfate ion, sulfuric acid would be H2SO4. I'm adding 2 because there's a 2 minus charge on the sulfate ion that I didn't get the minus on there. So that tells me to add 2 H's. And in this case, 4 oxygens give me the 8. Here, 3 oxygens earn the 8 value. So it's which gets called 8, which gets called I, depends on the different polyatomic ion you're dealing with. So you typically have to remember one of these, but then you can get the other 8 if you know the system. So again, things like this, practicing with the system is important, but you do have to do some bare minimization. I encourage you to make flashcards of some of these and practice so that you do know these. Alright, so that's where we're going to cut it for right now in today's video, and we'll be back with more and look for some examples, some opportunities to practice this on some homework.